So just from last time, I'm going to remind you what an inverse trig function is. Inverse sine of x, for example, is the angle. No, so I wrote this down and then I kind of modified it a little bit. So when I think of inverse sine of x, my brain immediately says, oh, it's the angle that if we take sine of that angle, we get x. But then I was like, I should be a little more specific. It's the angle between negative pi over 2 and pi over 2. That if we take sine of that angle, we get the value of x. So for example, inverse sine of x equal to an angle is equivalent essentially to sine of that angle equaling x. But we should really say that the angle theta is between negative pi over 2 and pi over 2. And then I also wrote down, because I thought it was important, for inverse cosine of x, the angle is between 0 and pi. So for inverse sine and inverse tangent, the angles you get are between negative pi over 2 and pi over 2. For inverse cosine, the angle is between 0 and pi. And I don't want to get into it because that's what we're just about to get there. Yes, how does the range work if it's an arc sine contained within the cosine line question? That's an excellent question. It's literally on the other side of my whiteboard here. So we're about to get there. What I do want to point out though is inverse secant and inverse cosecant are a little weird and we're not going to really cover them. But what I will say is if you encounter them in the future, come ask me about them, because I will tell you there's actually not agreement in the mathematical world about what the range of inverse secant should be. Some people think the range of inverse secant should be essentially, angles in the first two quadrants like inverse cosine. But some people say the range of inverse secant is essentially 0 to pi. Other people think the range of inverse secant should be 0 to pi over 2 and then pi to 3 pi over 2. And there's a really good calculus reason for that. And I think it's more worth talking about when we get to calculus. So I'll just say now, if you see inverse cosecant or inverse secant later on in life, come talk to me about it. It's an interesting topic. It's kind of weird, but it's neat. So, and then just a few examples of valuing things. The inverse sine of -1 is negative pi over 2 because sine of negative pi over 2 is equal to -1. And again, the way I would really think about this problem if I was doing it is I would really just ask myself, oh, what's inverse sine of +1? Oh, that's positive pi over 2. And it's nice, right? Because for inverse sine, if you know what the positive value gives you, you know what the corresponding negative value gives you. Always works that way. Inverse sine of root 3 over 2 is pi over 3. And we automatically know inverse sine of negative root 3 over 2 is negative pi over 3. It's not so nice for cosine. Inverse cosine of root 3 over 2 is pi over 6 because cosine of pi over 6 is equal to root 3 over 2. And I will just tell you, I feel like I made a mistake here. That's a mistake. I'm going to fix that in a minute. I wrote the wrong thing. Inverse cosine of negative root 3 over 2, unfortunately, is not negative pi over 6. It's 5 pi over 6. It's the angle in the second quadrant that has the reference angle that goes with the positive value. So that's kind of a brief review of how inverse trig functions kind of work. Again, I'm going to say this as many times as I can. You're always looking for the angle. And if you take whatever the trig function is of that angle, you get the value that was the input. That's the whole idea with an inverse trig function. Okay, but now, yes, we would like to calculate some other things, like sine of the inverse cosine of 1/2. Well, this one's actually not terrible because we know what inverse cosine of 1/2 is. Inverse cosine of 1/2, that is pi over 3. So we can just do this one as sine of pi over 3, which is the square root of 3 over 2. Or if we hadn't remembered that, we could have actually drawn a triangle. So, well, actually, I'll just do the next one because that I think is a better idea. So here's the thing for the next one. I don't know what angle inverse tangent of -4/5 is. I know it's an angle. So I find it really helpful when I'm doing this to remind myself that, oh yeah, inverse trig functions of numbers are angles. I find that super helpful. So what that tells me is, oh, I know that tangent of theta is equal to -4/5. And that's literally the definition of what an inverse trig function says. If inverse tangent of -4/5 is equal to the angle, tangent of the angle is equal to -4/5. It's the whole story. So what am I going to do next? What I often do when it comes to trigonometry, I'm going to draw a triangle. And I think I picked numbers I didn't really want to, but that's okay. Sometimes that happens. So I know that tangent is opposite over adjacent. So it's going to be, now again, personally, I don't like to include the negative sign. I'm going to say it's 4/5. You might prefer to include the negative sign. That's also fine. Either way, I want to find this third side. So I know that 5 squared plus 4 squared or -4 squared, either way, 4 squared or -4 squared is going to be 16. That's going to equal x squared. 25 plus 16 is 41. So x is the square root of 41. So now all we have to do is look at this triangle to figure out, well, we have to do it. That's not quite all. Almost all we have to do is look at this triangle. So what is cosine of this angle? Well, we know that cosine is the adjacent over that hypotenuse. So cosine of this angle is going to be what over what? That's a good question, Faith. I'll address that in just one second. I like your question. But let me figure this out first, and then we'll kind of get there. So cosine of this angle is going to be 5 over the square root of 41. Almost that. And then we're going to rationalize it. 5 root 41. Okay, but now we have to think about for a second. What quadrant is the angle theta in? Okay, well, here's what we know. We know that inverse tangent, the outputs have to be between -pi/2 and pi/2. So let me ask you guys, inverse tangent of a negative number, is that going to end up being in the first quadrant or in the fourth quadrant? Right, yeah, exactly. Because inverse tangent of a negative means tangent of the angle has to equal negative. And we can't be in the first quadrant. Essentially, here's what you should remember all the time. If you're taking an inverse trig function of a negative number, that angle is never in the first quadrant. It's always in the other quadrant option, whether it's quadrant 4 for inverse tangent or inverse sine, or quadrant 2 for inverse cosine. It's kind of always the case. So since this angle is in quadrant 4, cosine of an angle in quadrant 4 is still positive. So that's how we deal with something like that. I just want to point out, because it seems like a good time to say it, if instead I was trying to find sine of the inverse tangent of -4/5, well, sine would be the opposite over the hypotenuse, which would be 4 over the square root of 41. I'm not going to rationalize it, just going to out of room. But since our angle is in quadrant 4, sine has to be negative. Okay, we'll do more examples, but I want to address Faith's question because I think it's a good question. How do I know the negative is like here instead of here? That's actually that's a very fair question that I don't think I have actually a good answer to when it's tangent. Yeah, in fact, So I guess, so here's how I could justify it. I don't think it's particularly important. No, I guess it is. Yeah, so I would say typically we default to putting the negative in the numerator. And one way you can justify it here is because, well, this angle is really in quadrant 4 because it's inverse tangent of a negative. So if I was actually like drawing it in the standard position, my angle would be somewhere down here, like that. And we would have gone, so actually, I think I take it back. I can't justify it. I'm kind of, I don't want to say wrong because it's not really wrong. It's just, if you were really thinking about it, the 4 would be here and the -5 would be there. So that's a really excellent question, Faith. Like, good job. I think that's awesome, right? If you were really kind of drawing this the right way, you would put the negative here and the positive here. And that's really an example of why I don't think about it, right? Because it doesn't end up really mattering. I mean, it matters a little, but it doesn't matter as long as we at the end are like, okay, I know the angle is in quadrant 4. So I know sine should be negative. I know cosine should be positive. So that's why I typically just don't even draw the negative sign because I don't want to worry about that. But yeah, you're right. Like you if you were kind of putting a negative somewhere, you totally would actually put it on the -5. Good call. Usually when we're doing this, the answer I thought I was going to give you, well, in fact, let's do another example, and then we'll talk about why I thought I was going to give you a different answer. So let's look at something like.
Wait, so is like for the first one we did cosine and then like tangent inverse is 5 to the square root of 41 over 41. Is that the answer to the whole thing, or is it the answer to the inverse tangent?
This is the answer to cosine of the inverse tangent. So this is our answer to the whole thing.
Okay.
And in fact, I also want to point out, we never actually found inverse tangent of -4/5. And that's just the nature of the problem. We don't need to. We weren't asked to. We found cosine of it by using the triangle. But it's a really good question. Yeah. So, yeah. And typically, unless it's a value that we automatically kind of know the angle for, most of the time when you evaluate something like cosine of inverse tangent of something or sine of inverse cosine of something, most of the time you're not actually going to find out what the angle is. That's okay. So let's look at some more examples. So let's say we wanted to do, sure, let's look at this one. Let's look at a kind of a nicer example, actually. Let's do sine of inverse cosine of -4/5. So I'm going to ask everybody, oh, wait, why is that? Why is the tan theta? Not. Oh, because it's not tangent. It's inverse tangent. So I want to remind everybody, and I know I just erased the other side of the board, right? So, right, inverse tangent of a number, it's over here, right? Inverse tangent of any number, -4/5, is that what we got, right? Inverse tangent of -4/5 is the angle that if we take tangent of it, we get -4/5. So that's what's going on there. That's why I'm saying, oh yeah, inverse tangent of -4/5 is an angle. And it's the angle that if I took tangent of it, I would get -4/5, except I didn't write the name. That's what's going on there. So this is and I'm going to say the same thing here. Inverse cosine of -4/5 is an angle. It's the angle that if we take cosine of it, we get -4/5. And now here I would point out, just because I want to. Here, the negative would go on the leg there if you wanted to write it. Again, I'm not going to write it because it's more trouble than it's worth. But what I was thinking was going to happen previously was that we were going to have a hypotenuse side, and you never put the negative on the hypotenuse. The negative, if there is a negative, always goes on one of the legs because you're kind of either going negative x or negative y. But again, not what we had before. So I need to find the third side of that. 4 squared plus x squared equals 5 squared. We already know what it's going to be. We know it's going to be 3, right? This is your typical 3, 4, 5 triangle. X squared is 25 minus 16. X squared is 9. X is the square root of 9, which is 3. It's not drawn very well, right? The long side is drawn as the short side, so not to scale. That's okay. So now, sine of this angle, so I'm just writing again because I'm silly, is going to be equal to, well, if I look at the triangle, sine of that angle is 3/5. The Pythagorean triples you should be aware of, I think, are the 3, 4, 5 triangle and any multiple of it, like the 6, 8, not for like the test specifically, just in general, 6, 8, 10. And then the other one that pops up quite frequently is the 5, 12, 13. These are the ones you should know for now, I think. So, cool. Now let me ask you guys. This angle, inverse cosine of negative 4/5, is it in quadrant 1 or quadrant 2? Definitely 2, right? Inverse cosine of negative 4/5 can't be in quadrant 1 because it's inverse cosine of a negative number. So this is the angles in quadrant 2, which means sine of that angle should be positive 3/5. But if I ask for tangent of inverse cosine of negative 4/5, well, tangent would be the opposite over the adjacent. But since the angle is still in quadrant 2, the answer would be negative. Let's see. And it's kind of a lot of the same stuff. So we can do one more example, but then we should move on to, actually, I should probably stop there and move on to the other part of class because there is a lot of things to say. So they're not too terrible. Really, all you have to do for these is draw the triangle for the angle that you're taking sine or cosine or tangent or whatever trig function of. So the other thing we want to talk about today, which is very related to inverse trig functions, is solving trigonometric equations. Like the following. So typically, people usually say, solve the following for x between 0 and 2 pi. X greater than or equal to 0 is strictly less than 2 pi, meaning we're only looking for answers within one period. We don't need to find all the other, right? Like, so if, for example, if pi was an answer, we don't also need to say 3 pi and 5 pi and 7 pi because it's good enough to say pi. So we're going to solve the following. 2 cosine of x plus 1 equals to 0. And typically what we're going to do is we're going to isolate the trig function. So I'm going to subtract 1 from both sides and then divide both sides by 2. So here's the deal. We're trying to find where cosine of x is equal to negative 1/2. And it would be not wrong to think of this as thinking about that the inverse cosine of -1/2. All right, is it, well, it's in quadrant 2. Is it 5 pi over 6 or is it 2 pi over 3? I think it's 2 pi over 3. Because cosine of 2 pi over 3 is -1/2. It's really cosine of pi over 3 is 1/2 is what I'm actually thinking of. Okay, but here's what I want to emphasize. The answer here is not just 2 pi over 3. It is definitely one of the answers. But there's another answer. There's another answer in the third quadrant with the same reference angle, 4 pi over 3. And again, right, I like to think of this as kind of the difference between, so this here is like solving x squared equal to 9. There are two solutions. X equal to +3, x equal to -3. Whereas taking the inverse cosine of -1/2 is like taking the square root of 9. The only answer there is +3. And I'll just remind you guys that when you solve this, you get x equal to plus or minus the square root of 9. But the square root of 9 itself is +3. And we put the plus or minus on there so that we get both the positive and the negative solution. So finding the inverse trig function of a number gives you one angle. Solving or finding all of the solutions to cosine of x equal to -1/2, we typically get multiple solutions because there are multiple angles within one full period where cosine is equal to -1/2. You can also even see it if you think about the graph of cosine. By the way, I did finish grading your previous homework assignment, so you should go look at whatever comments I gave you guys. But I just want to point out here, right? Like, look, here is the graph of cosine of x. And here is the value y equal to -1/2. And oh, look, right there, and right there in quadrant 2 and quadrant 3, right? This is Q1. Q2, Q3, Q4 at 2 pi over 3 and 4 pi over 3. That's exactly where the cosine of x is equal to -1/2. And you can kind of look and say, oh, well, if I set cosine equal to anything between -1 and 1, I'm probably going to get two answers. Because any horizontal line you draw that's not actually -1 or not +1, you're going to get two places where it hits the cosine graph. I will also mention, just because we're saying right now, if someone said, find the solution to this, cosine of x equal to -1, there would only be one solution, x equal to pi. Yeah, excellent. Someone just wrote, I didn't even realize each quadrant is a quarter of the period. But if you think about the words, right, it totally makes sense. A quadrant is a quarter. A quarter is a quadrant. So that's why I really like to think about breaking the graph of cosine or sine up into 4 equal quarters, because you're just thinking about the 4 quadrants. In the first quadrant, cosine is positive. In the second quadrant, cosine is negative. In the third quadrant, cosine is negative. In the fourth quadrant, cosine is positive. How nice. I do want to also point out, if someone said solve cosine x equal to +1, technically you only get one solution because of the way we define things, right? We said our solution should be between x and 2 pi, but not actually equal to 2 pi. So our solution here is just x equal to 0 and nothing else, not x equal to 2 pi. But if you accidentally include 2 pi, it's fine. I won't really care that much. But I just want to mention that sometimes people are like, oh yeah, we only want one full revolution and not like the same point twice, which means we don't want the angle 0 and the angle 2 pi because they technically go to the same point. All right, let's look at some more examples. So sometimes the hard part with solving these kind of trigonometric equations isn't so much figuring out the angles, is doing the arithmetic beforehand to get a value that looks familiar. So let's say I wanted to solve something like 3 cosecant of theta is equal to the square root of 12. And again, our angle should be between 0 and 2 pi. Well, it's pretty funky. I mean, I should probably first isolate cosecant, but maybe even first, actually, I should simplify the square root of 12. So the square root of 12 is equal to the square root of 4 times 3. And the square root of 4 is 2. So really we have 3 cosecant of theta equal to 2 root 3. And then I can divide both sides by 3 and say that cosecant of theta is equal to 2 root 3 over 3. Honestly, this looks terrible to me. I never remember what angle cosecant is equal to anything at. I would probably flip these both over. I would probably say cosecant, no, that's 1 over sine. And then if I flip both sides, I can say that sine of theta is equal to 3 over 2 root 3. And then you can either just say 3 divided by the square root of 3 is the square root of 3. Or if you don't like that, you can also rationalize and multiply both the top and bottom by the square root of 3, which is going to give you 3 root 3 over 2 times 3. And yes, 2 times 3 is 6, but I'd rather just cancel the 3 there and the 3 there and get the square root of 3 over 2. I'm like, oh, okay, square root of 3 over 2. I know where sine is equal to square root of 3 over 2. The angle in the first quadrant is pi over 3. But then there's also an angle in, well, I want sine to be positive. So I know I also need an answer that is in quadrant 2, because sine is still positive in quadrant 2. So it's going to be the angle in quadrant 2 that has pi over 3 as its reference angle. So once you know one of the answers, all the other answers typically should have the same reference angle. So if you know one of your answers is 5 pi over 6, you know your other answer is something pi over 6. It's a 7 pi over 6 or 11 pi over 6 or 1 pi over 6. Just depends on kind of what you're working with. All right. Really, it's just more examples. Also, it is hot in here. Where's my little remote? There it is. I'm going to turn up the AC. Okay. So let's see here. What do we got? Another one. Let's say I want to solve, instead of 2 cosine x plus 1 equal to 0, now I have 2 cosine squared x minus 1 equal to 0. So don't get fooled by this one. I start solving for cosine. I have 2 cosine squared x equal to positive 1. And then divide both sides by 2. I have cosine squared of x equal to 1/2. And this is where it's easy to make a mistake. I know that cosine of x equal to 1/2 is the normal thing to look for. And I know that cosine of pi over 3 is equal to 1/2. But I don't have cosine, I have cosine squared. So what I need to do is actually take the square root of both sides. Square root of cosine squared is going to give me cosine. And now I actually should put on a plus or minus here. And the square root of 1 over 2 is the square root of 1 over the square root of 2. But the square root of 1 is just 1. And 1 over root 2 is really the square root of 2 over 2. And let me help my cat out here. I know. Here we go. Everyone, here's the cat. She's very lovely. Oh, yes. Great cat. Okay. You can go outside again. I'm scared. We're done. She was hiding here while there was some people in the house. So, okay. What angle always goes with root 2 over 2? I know more cat content would be preferred to math. I agree, but we got to do the math. Sorry. And yeah, she usually just runs away when I start talking to you guys because she doesn't like to hear me like being loud. But back to the math. Yeah, pi over 4, exactly. Now here's the thing that's nice about this. We're looking for all the angles where cosine is either equal to positive root 2 over 2 or negative root 2 over 2. When you want the trig function to be positive or negative, you're going to get the angle, all the angles in every quadrant that have pi over 4 as a reference angle. So we can say kind of right off of that, oh, our answers are going to be pi over 4 and 3 pi over 4 and 5 pi over 4 and 7 pi over 4. Because we want the answers in quadrant 1 where cosine is positive, in quadrant 4 where cosine is positive, and in quadrant 2 and 3 where cosine is negative. Because right, we really want to, we really want cosine squared of x to equal 1/2. And it doesn't matter if cosine is negative or positive, because when you square it, it's going to become positive. So yeah, whenever you're solving like a trig function squared equal to something, you typically get answers in every quadrant, which is nice. It makes it kind of easy to, how did I get the square root 2 over 2? Sure. I took 1 over root 2 and I rationalized it. I multiplied it by the square root of 2 over the square root of 2. And that's going to be the square root of 2 times 1. And the square root of 2 times the square root of 2 is just 2. Got more examples to do. All the rumors, I got the new song stuck in my head. All the rumors are true. Not really. None of the rumors are true. But what rumors? Okay, so let's solve this one. Secant of theta minus 2 equals 0. Whenever you're solving these, you typically want to isolate the trig function. Secant of theta equals 2. It's not the way my brain does it, right? Secant of theta is 1 over cosine of theta. 2, if you really want, you can say it's 2 over 1, but then reciprocals. Cosine of theta equals 1/2. I feel like this is probably more work than you actually need to show, but I'm showing all the work. And then we know the angles we're looking for are pi over 3 and something pi over 3. What pi over 3? 2 pi over 3? 4 pi over 3? 5 pi over 3? Which one is it? Well, I'm looking for quadrant 4. Which means I want it to be not 1 pi over 3, not 2 pi over 3, not 4 pi over 3, but 5 pi over 3. Okay, I still got 10 minutes. I got 10 whole minutes. You guys can't see it, but I'm dancing back here. Poorly, very poorly. But yeah, I was dancing back there. Maybe you could kind of see it. I don't know. You probably could. Now that I'm looking at it, like, oh, you probably could totally see you kind of dancing. Oh, that's all right. Gotta have fun. What else are you gonna do? Let's see. So let's try solving this one. 3 tangent squared theta equals 1. And now here's what I want you to see. Now I want you to be so I don't want to say this is 100% true all the time, but if you just have a trig function squared and like no other trig functions, like there's not another tangent somewhere, if I just have like tangent squared equal to something, you're going to get answers in 4 quadrants. So I've got tangent squared theta equal to 1/3, and then I'm going to take the square root of both sides. Square root of tangent squared theta is going to be plus or minus the square root. Square root of tangent squared is just tangent. Now, square root of 1/3, I really do encourage you to think about it as the square root of 1 over the square root of 3, which you should immediately simplify as just 1 over the square root of 3, because the square root of 1 is always 1. And then we should rationalize by multiplying by root 3 over root 3 to get plus or minus root 3 over 3. This is not required, but the reason I'm doing it is so that it looks like the thing I'm used to seeing. It's the same reason I rationalized the previous problem that I already erased. Because we're more used to seeing cosine equal to root 2 over 2 instead of 1 over root 2. So if you're like, oh, I know that tangent equal to 1 over root 3 is something, that's also fine. But I feel like most of you are probably used to seeing it this way, so you want to make it look like the thing you're looking for. Again, if you want it, so words. Tangent equal to root 3 over 3. I think that's the pi over 6 angle. Yeah, it's the pi over 6 angle. So I know that one of my angles is pi over 6. This tangent of pi over 6 is root 3 over 3. And then I'm going to actually go, I'm just going to write them all out. I'm going to write all of the angles in quadrants 1, 2, 3, and 4, whose reference angle is pi over 6. So we've got a 5 pi over 6. We've got a 7 pi over 6. And we've got an 11 pi over 6. And I will just point out these two in quadrants 1 and quadrant 3, that's where tangent of the angle is positive. And these two are where I ran out of room. It's where tangent of the angle is negative root 3 over 3. Bonus question. The inverse tangent of positive root 3 over 3 is which of these angles? The first one, the second one, the third one, or the fourth one? It's the first one. Inverse tangent of root 3 over 3 is pi over 6. But the point I want to make is that the inverse tangent of negative root 3 over 3 is none of those. It's negative pi over 6. So yeah, so if someone said like if someone just asked you to say solve tangent of theta equal to negative root 3 over 3, and I know I stopped writing it down, but the assumption we've been making every time is their angles are between 0 and 2 pi. If someone asks you to solve an equation like this, you should generally assume they mean this, even if they're stupid and forgot to write it down. But tangent equal to negative root 3 over 3, the answers would be 5 pi over 6 and 11 pi over 6. But the inverse tangent of negative root 3 over 3 is negative pi over 6. Which again is essentially the same as 11 pi over 6, but not exactly the same. They are different. They're coterminal. But just things to be aware of. Okay. Yeah, let's take a look at a couple more. I'm going to skip the next one because it's very similar to what we've just been doing. Actually, I'm not going to skip it. I'm going to start, but I'm not going to finish it. So let's say we were trying to solve 4 cosine squared theta minus 1 equal to 0. One way to go about this, which is what we've already been doing, is to just isolate cosine. So you could say one way is 4 cosine squared theta equal to 1, cosine squared theta equal to 1/4, and then the square root of that is cosine theta equal to plus or minus the square root of 1/4, which is plus or minus 1/2. And let me see. 1 second. Let me finish this, and then I can answer that question. Or you could do this one by factoring. You could factor it as a difference of squares. It's 2 cosine theta minus 1 times 2 cosine theta plus 1 equals 0. And then this part leads us to cosine theta equals 1/2. And this part leads us to cosine theta equals -1. So either way you go about this, you're still getting to the same place where you're trying to find all the solutions to cosine theta equals plus or minus 1/2, or cosine theta equals 1/2 or -1/2. Either way, you're going to get all the pi over 3 angles. So the end, I said I'm not going to finish this problem. Totally. The answer would be these 4 angles. The point I want to make with this is sometimes you need to factor the things instead of just solving. Somebody asked, though, how do you work backwards from pi over 6? We have to get the reference angle from 5 pi over 6, but don't know how to go back. I guess I'm not really sure what the question is asking there. What I did was I said, I know that I'm trying to solve tangent theta equals √3/3, and it can be positive or negative. So I'm going to get all the angles in every quadrant that have pi over 6 as a reference angle, which include the angles 5 pi over 6, 7 pi over 6, and 11 pi over 6. Let me go back. I don't want to go back. Yeah, I'm not really sure what the question is saying, but I'm happy to address it later if it is clarified. Okay, this is an example I'm going to skip, but I want to get to these last 1 or 2 examples because things can get things can get a little bit tricky if you've got, well, like in this next example. I'm probably going to ask for a few extra minutes so I can do one more example. Let's say I want to solve sine squared of x minus sine of x equal to 0. Ooh. So here's the thing. If you've got the same trig function and you've got different powers of it, you're going to have to factor. I can totally factor out a sine of x from each of these. And say this is sine of x times sine of x minus 1. So then I either need sine of x to equal 0 or sine of x minus 1 to equal 0. Okay, well, we know where sine is equal to 0. Sine is equal to 0 when x is equal to 0 or pi, right? Unit circle, quadrantal angles. I labeled that one wrong. That's a 1, 0, not a 0, 1. So we can see that sine, the y coordinate, is equal to 0 at 0 radians and at pi radians. And I'm not going to include 2 pi because we usually don't include 2 pi. And then here I'm going to solve this. I'm going to have sine of x equal to 1, which is when x is equal to pi over 2 radians. So this problem would have 3 answers, 0, pi, and pi over 2. And I know it's 2:20, but I want to do one more quick example, and then I will stop. And I will mention there are extra, so there's another couple pages worth of examples. So if you're looking for more examples, I would encourage you to look at the notes that are posted for class K. And that's specifically the ones that are kind of like notes I actually used in class, right? Not like the other ones. Let me give you one more example, and then I will stop. And then you can ask me other questions if you want. You can come to office hours. Let's say I want to solve, yeah, sure. I want to solve 2 sine squared x plus 3 sine x plus 1 equal to 0. And so the idea here is that this is factorable like a quadratic. This is going to factor as 2 sine of x plus 1 times sine of x plus 1. And if you were to FOIL this out, you get 2 sine times sine, which is 2 sine squared. 2 sine times 1, which is 2 sine. Sine times 1, which is another sine, and 2 sine plus sine is 3 sine. And then 1 times 1. So it totally does multiply out to that. And then you would do the usual thing when you have things that multiply to 0. You have things that multiply to 0, which is why we set things equal to 0 like all the time. If they multiply to 0, either one of them has to be 0. So either 2 sine of x plus 1 has to equal 0, or sine of x plus 1 has to equal 0. So solving this one, 2 sine of x equals -1. Sine of x equals -1/2. Solving this one, I know I'm not done there, but I'm just getting into where I've isolated sine. Sine of x equals -1. So for this one, sine of x equals -1/2. Well, I know the reference angle is pi over 3. Because I know that sine of pi over 3 is +1/2. So I need my actual angles to be in the quadrants where sine is negative, which is quadrant 3 and quadrant 4. Sine of 4 pi over 3 is -1/2. Sine of 5 pi over 3 is -1/2. And then sine of x equal to -1, that's one of those quadrantal angles. Specifically, I'm looking at that point there, where the angle is 3 pi over 2. So this equation would also have 3 answers between 0 and 2 pi. You know what? Yeah, I boned that one. Sorry. Excellent point. Whew. So just want to mention, I am human. I make mistakes sometimes. I apologize. I don't try to make mistakes. Like I definitely was like, oh, I'm testing you guys. No, I was not testing you guys. I totally was like, oh yeah, sine of pi over 3 is 1/2. No, it's not, right? And so, right, it's good to check your work or have other people check your work, right? Pi over 3, that's the bigger angle than pi over 6. And the opposite side of pi over 3 is √3. The opposite side of pi over 6 is the 1, and the hypotenuse is 2. So the reference angle is not pi over 3. It is indeed pi over 6. Thank you for calling me out on that. Anytime you think I made a mistake, please let me know. So these would be the right angles if it was sine of x equal to -√3 over 2. But they are not the right angles for sine of x equal to -1/2. The right angles would be, so in quadrant 3, it's not pi over 6, it's not 5 pi over 6, which in quadrant 2, it's 7 pi over 6. And in quadrant 4, it would be 11 pi over 6. Thanks, Nye. I appreciate the catch there. Okay, so there are more examples of solving trigonometric equations like this in the notes.